Hi everyone, I hope this video finds you well, and today we're going to talk about the derivation of the equations for the three types of inhibition being emphasized in our class, particularly competitive, uncompetitive, and the non-competitive. So let's start. So first, for competitive inhibition, as the name suggests, the inhibitor competes with the substrate. So there are three steps involved. So there will be two reversible and one irreversible. So first would be the production of the enzyme substrate complex, and the second would be the enzyme inhibitor complex. So for the purpose of this derivation, we're going to name the five rate constants by number. So for the first step, the rate constant would be renamed later for simplification as K sub S, and for the second step for the enzyme inhibitor complex, renamed later as K sub I. So that would be the rate constant of the backward over the rate constant of the forward reaction. And last but not the least, that would be our product rate constant K sub 5. And let's assign the first equation to our product velocity, which is V sub P equals K sub 5 times the concentration of the enzyme substrate. Now, our first assumption would be that the total enzyme content remains constant all throughout. And then this equation would have to give us an idea of what we are going to look for. And because our product rate equation requires us to express the concentration in terms of the enzyme substrate, that's what we're going to do with the rest of these concentrations. And that is the use of our equations. So this is forward equals backward reactions for the two steps. And then we're going to transpose. So that will arrive with our ES term. So here, we see that there are two enzyme concentrations for the first two steps. So we can deduce that the first and the second would be equal in terms of ES through EI, so that we can get the term for EI. And then the concentration enzyme we're going to use would be the one in terms of ES, so the first one. Okay, so far so good. Now we're going to plug them in. So this is for the enzyme concentration and this is for the enzyme inhibitor complex. Now we're going to simplify further by taking out the common variables found in each term, which is why we're left with this. And now, since we can express this whole thing as the whole numerator, this in turn tells us this is our denominator. So that we'll be able to simplify since our ES is on the right side and we need the ES isolated. We're going to multiply the whole equation with this denominator. That's why we arrive at this equation. So now we can already take out the ES term in this whole expression here in the right side. So ES will be out, and this is the whole expression that we need to divide to the other side so that the enzyme substrate concentration would be isolated. So we can see that here in the next. So this will be here down in the denominator, and then we're left with here. So now we further simplify, make sure that the remaining constants are that of the inhibitor for the substrate. So we are going to multiply the reciprocal of K sub 1 because that's the common here in the numerator and in the denominator. So now we have our ES term, but we haven't renamed the rate constants yet. Now further, we're going to plug in this whole. So before plugging it in, it's best that we rename them. So we already changed it to K sub S and K sub I. So you're wondering why? Because K sub 3 and K sub 4 here are inverse. And remember that K sub 4 is our numerator or our backward reaction. So that's the product rate concentration. So we expect, of course, K sub I to be in the denominator. Now we're going to plug this in. So we go back to our product rate equation. So this is the whole whiteboard, guys, in case you're curious. So now let's go back to our first equation. Then we assign V sub P, or the product velocity, as our velocity. Then we have our product constant here. So plugging it in, this would be our equation. So take note that this is only for the purpose of the derivation, how we technically arrive at this by algebraic manipulation. So in instances, we're going to prove that this equation is exactly what it's supposed to function, especially in higher or further proving methods. So this term here, or this variable, would have to be our maximum velocity, and this would have to be our Michaelis-Menten constant. That if the data given would verify that indeed it is. So that would be all for competitive inhibition.